Now that Python is installed and running, we can immediately start using it. This is a good way to get to know the language, as well as a useful tool for experimentation and quick testing during normal development. This Python command line environment is a read, eval, print loop. Python will read whatever input we type in, evaluate it, print the result, and then loop back to the beginning. You'll often hear it referred to as simply the REPL. When started, the REPL will print some information about the version of Python you're running, and then it will give you a triple arrow prompt. This prompt tells you that Python is waiting for you to type something. Within an interactive Python session, you can enter fragments of Python programs and see instant results. Let's start with some simple arithmetic. 2 plus 2 is 4. As you can see, Python reads our input, evaluates it, prints the result, and loops around to do the same again. 6 times 7 is 42. We can assign to variables in the REPL, x equals 5, and print their content simply by typing their name. We can also refer to variables and expressions, such as 3 times x. Within the REPL, you can use the special underscore variable to refer to the most recently printed value, this being one of very few obscure shortcuts in Python. Or you can use the special underscore variable in an expression. Remember though that this useful trick works only at the REPL. The underscore doesn't have any special behavior in Python scripts or programs. Notice that not all statements have a return value. When we assigned 5 to x, there was no return value, only the side effect of bringing the variable x into being. Other statements have more visible side effects. Try print hello Python at the prompt, followed by return. You'll see that Python immediately evaluates and executes this command, printing the string hello Python and returning you to another prompt. It's important to understand that the response here is not the result of the expression evaluated and displayed by the REPL, but is a side effect of the print function. As an aside, print is one of the biggest differences between Python 2 and Python 3. In Python 3, the parentheses are required, whereas in Python 2 they were not. This is because in Python 3, print is a function call. More on functions later. At this point, we should show you how to exit the REPL. We do this by sending the end of file control character to Python, although unfortunately the means of sending this character varies across platforms. If you're on Windows, press Ctrl-Z to exit. If you're on Mac or Linux, press Ctrl-D to exit. If you regularly switch between platforms and you accidentally press Ctrl-Z on a Unix-like system, you will inadvertently suspend the Python interpreter and return to your operating system shell. To reactivate Python, making it a foreground process again, simply run the fg command, and press enter a couple of times to get the triple arrow Python prompt back. Start your Python 3 interpreter using the Python or Python 3 command for Windows or Unix-like systems respectively. The control flow structures of Python, such as for loops, while loops, and if statements, are all introduced by statements which are terminated by a colon, indicating that the body of the construct is to follow. For example, for loops require a body, so if you enter for I in range 5, Python will change the prompt to 3 dots to request you provide the body. One distinctive, and sometimes controversial aspect of Python is that leading whitespace is syntactically significant. What this means is that Python uses indentation levels rather than the braces used by other languages to demarcate code blocks. By convention, contemporary Python code is indented by 4 spaces for each level, so we provide those 4 spaces and a statement to form the body of our loop, x equals I times 10. Our loop body will contain a second statement, so after pressing return, at the next 3 dot prompt we enter another 4 spaces, followed by a call to the built-in print function. To terminate our block, we must enter a blank line into the REPL. With the block complete, Python executes the pending code, printing out the multiples of 10 less than 50. Looking at a screen full of Python code, we can see how the indentation clearly matches, and in fact must match the structure of the program. Even if we replace the code by grey lines, the structure of the program is clear. Each statement terminated by a colon starts a new line and introduces an additional level of indentation, which continues until a dedent restores the indentation to a previous level. Each level of indent is typically 4 spaces, although we'll cover the rules in more detail in a moment. Python's approach to significant whitespace has 3 great advantages. First, it forces developers to use a single level of indentation in a code block. This is generally considered good practice in any language because it makes code much more readable. Second, code with significant whitespace doesn't need to be cluttered with unnecessary braces, and you never need to have a code standard debate about where the braces should go. All code blocks in Python code are easily identifiable and everyone writes them the same way. Third, significant whitespace requires that a consistent interpretation must be given to the structure of the code by the author, the Python runtime system, and future maintainers who need to read the code. So you can never have code that contains a block from Python's point of view, but which doesn't look like it from a cursory human perspective. The rules for Python indentation can seem complex, but are straightforward in practice. The white space you use can either be spaces or tabs. The general consensus is that spaces are preferable to tabs, and 4 spaces has become a standard in the Python community. One essential rule is never to mix spaces and tabs. The Python interpreter will complain and your colleagues will hunt you down. You are allowed to use different amounts of indentation at different times if you wish. The essential rule is that consecutive lines of code at the same indentation level are considered to be part of the same code block. There are some exceptions to these rules, but they almost always have to do with improving code readability in other ways, for example by breaking up necessarily long statements over multiple lines. This rigorous approach to code formatting is programming as Guido indented it. The philosophy of placing a high value on code qualities such as readability gets to the very heart of Python culture, something we'll take a short look at now. Many programming languages are at the center of a cultural movement. They have their own communities, values, practices, and philosophy, and Python is no exception. The development of the Python language itself is managed through a series of documents called Python Enhancement Proposals, or PEPs. One of the PEPs, called PEP 8, explains how you should format your code, and we follow its guidelines throughout this course. It is PEP 8 which recommends we use 4 spaces for indentation in new Python code. Another of these PEPs, called PEP 20, is called the Zen of Python. It refers to 20 aphorisms describing the guiding principles of Python, only 19 of which have been written down. Conveniently, the Zen of Python is never further away than the nearest Python interpreter, as it can always be accessed from the REPL by typing import this. Throughout this course we'll be highlighting particular nuggets of wisdom from the Zen of Python in moments of Zen to understand how they apply to what we have learned. As we've just introduced Python's significant indentation, this is a good time for our first moment. Readability counts. Clarity matters, so readability makes for valuable code. In time, you'll come to appreciate Python's significant whitespace for the elegance it brings to your code and the ease with which you can read others. As mentioned earlier, Python comes with an extensive standard library, an aspect of Python often referred to as batteries included. The standard library is structured as modules, a topic we'll discuss in depth later in the course. What's important at this stage is to know that you gain access to standard library modules using the import keyword. The basic form of importing a module is simply the import keyword followed by a space and the name of the module. For example, let's see how we can use the standard library's math module to compute square roots. At the triple arrow prompt we type import math. Since import is a statement which doesn't return a value, Python doesn't print anything if the import succeeds, and we're immediately returned to the prompt. We can access the contents of the imported module by using the name of the module, followed by a dot, followed by the name of the attribute in the module that you need. Like many object-oriented languages, the dot operator is used to drill down into object structures. Being expert Pythonistas, we have inside knowledge that the math module contains a function called square root. Let's try to use it. But how can we find out what other functions are available in the math module? The REPL has a special function, help, which can retrieve any embedded documentation from objects for which it has been provided, such as standard library modules. To get help, type simply help. We'll leave you to explore the first form for interactive help in your own time. We'll go for the second option and pass the math module as the object for which we want help. You can use the spacebar to page through the help, and if you're on Mac or Linux, use the arrow keys to scroll up and down. Browsing through the functions, we can see there's a math function for computing factorials. Press Q to exit the help browser and return us to the Python REPL. Practice using help to request specific help on the factorial function. Press Q to return to the REPL. Let's use the factorial function, which accepts an integer and returns an integer. Notice how we need to qualify the function name with the module namespace. This is generally good practice, as it makes it abundantly clear where the function is coming from. That said, it can result in code that is excessively verbose. Let's use factorials to compute how many ways there are to draw 3 fruit from a set of 5 fruit using some math we learned in school. This simple expression is quite verbose with all those references to the math module. The Python import statement has an alternative form that allows us to bring a specific function from a module into the current namespace. This is a good improvement, but it's still a little long-winded for such a simple expression. A third form of the import statement allows us to rename the imported function. This can be useful for reasons of readability or to avoid a namespace clash. Useful as it is, we recommend that this feature be used infrequently and judiciously. Remember that when we used factorial alone, it returned an integer, but our more complex expression for combinations is returning a floating point number. This is because we've used Python's floating point division operator, the single /. We can improve our expression, since we know it only ever returns integral results, by using Python's integer division operator, which is a double /. What's notable is that many other programming languages would fail on the above expression for even moderate values of n. In most programming languages, regular garden variety signed integers can only store values less than 2 to the power 31. However, factorials grow so fast that the largest factorial you can fit into a 32-bit signed integer is 12 factorial, since 13 factorial is too large. In most widely used programming languages, you would need more complex code or more sophisticated mathematics merely to compute how many ways there are to draw 3 fruits from a set of 13 fruits. Python encounters no such problems and can compute with arbitrarily large integers limited only by the memory in your computer. Let's try the larger problem of computing how many different pairs of fruit we can pick from 100 different fruits, assuming we can lay our hands on so many fruit. Just to emphasize how large the size of the first term of that expression is, calculate 100 factorial on its own. It's a number vastly larger even than the number of atoms in the known universe, with an awful lot of digits. If, like me, you're curious to know exactly how many digits, we can convert our integer to a text string and count the number of characters in it, like this. Let's move on and look at integers, strings, and other built-in types in more detail. Python comes with a number of built-in data types. These include primitive scalar types like integers, as well as collection types like dictionaries. These built-in types are powerful enough to be used alone for many programming needs, and they can be used as building blocks for creating more complex data types. In this section we'll cover the basic scalar built-in types. int, float, non, and bool. We'll provide basic information about these now, showing their literal forms and how to create them. We've already seen quite a lot of Python integers in action. Python integers are signed and have for all practical purposes unlimited precision. Integer literals in Python are specified in decimal, but may also be specified in binary with a 0b prefix, octal with a 0o prefix, or hexadecimal with a 0x prefix. We can also construct integers by a call to the int constructor, which can convert from other numeric types such as floats to integers. Note that rounding is always towards 0. We can also convert strings to integers. To convert from base 3, use int and then 10000 as a string, comma 3. Floating point numbers are supported in Python by the float type. Python floats are implemented as IEEE 754 double precision floating point numbers with 53 bits of binary precision. This is equivalent to between 15 and 16 significant digits in decimal. Any literal number containing a decimal point or a letter E is interpreted by Python as a float. Scientific notation can be used, so for large numbers, such as the approximate speed of light in meters per second, 3 times 10 to the 8, we can write 3e8. And for small numbers, like Planck's constant, 1.616 times 10 to the minus 35, we can enter 1.616 e minus 35. Notice how Python automatically switches the display representation to the most readable form. As for integers, we can convert to floats from other numeric or string types using the float constructor, from an int and from a string. This is also how we create the special floating point values nan, or not a number, and also positive and negative infinity. The result of any calculation involving int and float is promoted to a float. Python has a special null value called non with a capital N. Non is frequently used to represent the absence of a value. The Python REPL never prints non results, so typing non into the REPL has no effect. Non can be bound to a variable name just like any other object. And we can test whether an object is non by using Python's is operator. We can see here that the response is true, which brings us conveniently onto the bool type. The bool type represents logical states and plays an important role in several of Python's control flow structures, as we'll see shortly. As you would expect, there are two bool values, true and false, both with initial capitals, and also a bool constructor which can be used to convert from other types to bool. Let's look at how it works. For integers, 0 is considered falsy and all other values truthy. We see the same behavior with floats, where only 0 is considered falsy. When converting from collections, such as strings or lists, only empty collections are treated as falsy. Converting from lists, which we'll look at shortly, and strings, In particular, you cannot use the bool constructor to convert from the string representations of true and false, because the string false is not empty. These conversions to bool are important because they are widely used in Python if statements and while loops, which accept bool values into the condition. Bool values are commonly produced by Python's relational operators, which can be used for comparing objects. The relational operators are sometimes called the comparison operators. These include value equality and inequality, less than or equal to, and greater than or equal to. Two of the most widely used relational operators are Python's equality and inequality tests, which actually test for equivalence or inequivalence of values. That is, two objects are equivalent if one could be used in place of the other. We'll learn more about the notion of object equivalence later in the course. For now, we'll simply compare integers. Let's start by assigning or binding a value to a variable g. We test for equality with a double equals operator, or for inequality using the not equals operator. We can also compare the order of quantities using the so-called rich comparison operators, less than, greater than, less than or equal to, and greater than or equal to. Now we've examined some basic built-in types, we'll look at two important control flow structures which depend on conversions to the bool type. While loops, but first if statements. Conditional statements allow us to branch execution based on the value of an expression. The form of the statement is the if keyword, followed by an expression, terminated by a colon to introduce a new block. The expression is converted to bool, as if by the bool constructor. Let's try this at the REPL. Remembering to indent 4 spaces within the block, we add some code to be executed if the condition is true. Followed by a blank line to terminate the block, at which point the block will execute, because self-evidently the condition is true. Conversely, if the condition is false, the code in the block does not execute. Because the expression used with the if statement will be converted to bool, just as if the bool constructor had been used, this form is exactly equivalent to this form. Thanks to this useful shorthand, explicit conversion to bool using the bool constructor is rarely used in Python. The if statement supports an optional else clause, which goes in a block introduced by the else keyword, followed by a colon, which is indented to the same level as the if keyword. To start the else block in this case, we just omit the indentation after the 3 dots. For multiple conditions, you might be tempted to do something like this, nesting if statements. Whenever you find yourself with an else block containing a nested if statement like this, you should consider instead using Python's elif keyword, which is a combined else if. As the Zen of Python reminds us, flat is better than nested. This version is altogether easier to read. We'll quickly demonstrate it at the REPL. Now we've examined some basic built-in types, program, returning us to the REPL prompt. Python has two types of loop, for loops and while loops. We've already briefly encountered for loops back when we introduced significant whitespace, and we'll return to them soon. But right now, we'll cover while loops. While loops in Python are introduced by the while keyword, which is followed by a Boolean expression. As with the condition for if statements, the expression is implicitly converted to a Boolean value, as if it had been passed to the bool constructor. The while statement is terminated by a colon because it introduces a new block. Let's write a while loop at the REPL which counts down from 5 to 1. We'll initialize a counter variable called c to 5 and keep looping until we reach 0. Another new language feature here is the use of the augmented assignment operator to subtract 1 from the value of the counter on each iteration. Similar augmented assignment operators exist for the other basic math operators, such as plus and multiply. Because the condition, or predicate, will be implicitly converted to bool, just as if a call to the bool constructor were present, we could replace the above code with the following version. This works because the conversion of the integer value of c to bool results in true until we get to 0, which converts to false. That said, to use this short form in this case might be described as unpythonic, because referring back to the Zen of Python, explicit is better than implicit, and we place a higher value on the readability of the first form over the concision of the second form. While loops are often used in Python where an infinite loop is required. We achieve this simply by passing true as the predicate expression to the while construct. Now you're probably wondering how we get out of this loop and regain control of our REPL. We press Ctrl-C, which Python intercepts to raise a special exception which terminates the loop. We'll be talking much more about what exceptions are and how to use them later in the course. Many programming languages support a loop construct which places the predicate test at the end of the loop rather than at the beginning. For example, C, C++, C#, and Java support the do-while construct. Other languages have repeat until loops instead or as well. This is not the case in Python, where the idiom is to use while true together with an early exit facilitated by the break statement. The break statement jumps out of the loop, and only the innermost loop if several loops have been nested, continuing execution immediately after the loop body. Let's look at an example of break, introducing a few other Python features along the way. We start with while true for an infinite loop. On the first statement of the while block, we use the built-in input function to request a string from the user. We assign that string to a variable called response. We now use an if statement to test whether the value provided is divisible by 7. We convert the response string to an integer using the int constructor, and then use the modulus operator with the % symbol to divide by 7 and give us the remainder. If the remainder is equal to 0, the response was divisible by 7, and we enter the body of the if block. Within the if block, now 2 levels of indentation deep, we start with 8 spaces and use the break keyword. Break terminates the innermost loop, in this case the while loop, and causes execution to jump to the first statement after the loop, or in our case, the end of the program. Enter a blank line at the 3 dots prompt to close both if block and the while block. Our loop will start executing and will pause at the call to the input function, waiting for us to enter a number. Let's try a few. 12, 67, 34, and 28. As soon as we enter a number divisible by 7, the predicate becomes true, we enter the if block, and then literally break out of the loop to the end of the program,